Students, good morning. Good morning to one and all. This is Professor Chetan Jadhav from Mechanical Department, Jain College of Engineering, Belgaum. Students, yesterday we have started with module number 4, okay? And this will be your second lecture on module number 4 of your subject, Kinematics of Machines. And in the previous class, we have discussed what is exactly the working principle of a CAM, and we have discussed the definition of CAM, which is nothing but a CAM is a rotating machine element which gives a reciprocating or oscillating motion to another element which is known as follower. So this was a CAM to which we have given an input motion of a rotary type. Okay, this will be connected to a motor and it will be rotating, and the output motion we are getting from this follower, which may be in the form of a reciprocating type or sometimes it may be oscillating type. And we have discussed some features of this CAM. It means the type of contact between this CAM and the follower is a line or a point contact, and hence it forms a higher pair, correct? And the contact between these two elements is maintained with the help of a spring force, so which was discussed in the previous class. I have shown some animation also, and I have said one more thing, that the velocity of this CAM or the speed of this CAM is uniform. It is moving with uniform velocity. But as in case of a follower, the velocity may change at a different time. It means the follower has a non-uniform speed as per a requirement. And these are the three basic components of this CAM, the CAM and follower. The first one is a CAM, which acts as a driving member, and one more is a follower. So this acts as a follower. It means it is a driven member, and one more is a frame. Okay, so whatever the fixed elements are the guideways which supports this CAM and the guides the motion of the follower, they comes under frame. So these are the three basic components which were discussed in the previous class. And also we have started with the classification of followers. According to these three criteria, the first one is according to the shape of the follower. We have discussed the first one, that is a knife edge follower. After that we have discussed the roller follower, flat faced follower, spherical faced follower. So these four comes under the first criteria. So based on the type of or the shape of the follower, okay, we have discussed these four, and I have showed some animation also. And after that we have discussed according to the motion of the follower. If the type of motion the follower has it is of a reciprocating type, it comes under reciprocating follower. If the follower is oscillating, it comes under oscillating follower. Now also we have discussed the last one, that is according to the position of the follower. If the axis of the follower is passing through the center of the camshaft, that comes under radial follower. And the offset follower means the axis of the follower is slightly offset either towards right or left with respect to the center of the camshaft. It means in case of an offset follower, the follower axis will not follow or will not pass through the center of the camshaft. So this was also discussed in the previous class. And let me start with today's lecture. Again, it is a classification of CAMs. In the previous class, we have discussed the classification of followers, and in today's class, we are going to discuss with the classification of CAMs. Again, these are the three criteria based on which we are going to classify the CAMs. Just take the first one. So that is according to the type of follower motion. Just note down this. I'll give 30-second time. Just note down these classifications so that I can go ahead with the first one. The first criteria is according to the type of follower motion. So based on what is the kind of the motion the follower has. So we are going to classify into three types. First one is a dwell, rise, dwell, return, and dwell. In shortcut, it is called as a DR decamps. And the second one is dwell, rise, return, and again dwell. And the third one is rise, return, rise. Okay, I'll discuss what is exactly this dwell time, rising time, and returning time. So I'll start with the first one, that is DR decamps. So this is the first classification. So based on the type of follower motion. So you can see the graph. So this is the graph. So I can call it as a displacement diagram. Okay, this is a displacement diagram. Along the x-axis, I'm going to plot the cam rotation angle. I think you have seen the animation of the cam, correct? It will rotate from 0 degree to 360. So I'll plot the angle, that is the angular displacement of the cam along this x-axis. And along y-axis, I'll take the displacement of the follower. It means the distance traveled by the follower. So better I can show an animation. Yeah, just consider this animation. So this animation. You can see the angular displacement of this cam is starting from 0 degree to 360. It covers total 360 degree. So this, the angular displacement of the cam, I'll consider along x-axis. Okay, and as the cam starts rotating, the follower also starts moving in upward and downward direction. Correct? It means it is covering some distance. It is traveling through some distance. I can call it as a follower lift. Okay, so which is indicated with the alphabet S. Okay, the lift of the follower, or the distance that is traveled by this follower. For example, it is now, it is exactly at 0 mm. Then it will travel by 10 mm, 20, 30, 40, 50, 60. Okay, as the cam starts from 0 to 360, the follower also covers some distance. For example, the maximum distance is 40 mm. The distance that is traveled by this follower is 40 mm. Okay, so between 0 to 40, I'll plot the distance traveled by this cam, which is called as displacement of the follower. So this is the displacement of the follower along the y-axis. Okay, yeah. So you can see along the x-axis, I have plotted the cam rotation angle from 0 to 360, and along y-axis, I am to plot the displacement of the follower, or you can say lift of the follower, the distance traveled from 0 to 10 mm, 20, 30, and 40. Okay, the maximum I am taking the 40 mm. The distance traveled by follower is 40 mm. So this is indicated with the alphabet S. Okay, and one more thing is what are the different types of motions of the follower? Okay, there are three basic types of the follower movement. Okay, first one is the rise. Again, I'll go to the same animation so that I can explain, I can correlate the graph as per your convenient. Okay, so you can see whenever the follower is moving in an upward direction, I can call it as a rise. It means the follower is moving in upward direction, it is rising. It is moving away from this cap. It is called as a rise. After that, it will come down. You can see. After that, it will come down. So whenever the follower is moving in a downward direction, I can call it as a return. Okay, return. And between a rising time and a returning time, it will take some rest. So now it is under rest. Rise, return, rest. Rise, return, rest. It means in between rising and returning, it is taking some rest. It means there is no movement. Whenever there is no movement of the follower, I can call it as a dwell time. Okay, so this is the rise, return, dwell. Rise, return, and dwell. So these are the three basic types of a follower movement. Based on that, I can classify into different types. In that, the first one was this one. Okay. So if the follower movement, the displacement of the follower, so in the form of a dwell, it means initially whenever whenever the angle is 0 degree. Okay. For example, the total angle is 360. I'll consider during the first 30 degree of a cam rotation. During the first 30 degree of cam rotation, there is no movement of the follower. You can see the distance traveled of the follower is 0. Okay, so this is 0. I'll consider as a 30 degree. Whenever the cam is rotating from 0 to 30, there is no movement of the follower. It means the curve is flat. Correct? It means the follower is under rest. The follower is under rest, but the cam is rotating. So I can call it as a dwell period. There is no movement of the follower. After that, from 30 to 90 degree, you can say. Example, you just take example. After that, whenever the angle that is covered by the cam is from 30 to 90 degree. So in that time, you can see there is a rise of the follower. It means the follower is moving in upward direction. So through what is the distance from 0 to 40 mm? Okay, it means the follower is moving in upward direction. I can call it as a rise. And there are so many varieties of the followers. So in this case, after rising also it is under rest. There is no movement. For the next rotation of the cam, you can say 90 to 180. So there is no movement of the follower. It is under rest. Okay. So again, whenever the follower is under rest, again I'll call it as a dwell time. Okay. After that, from 180 to 270. So this is 0. So I consider this as a 30 and 90. Then this is a 180. I'll consider this as a 270. During this moment, during this cam rotation angle, you can see the follower is coming down. Okay, it means the distance, the follower is moving in a downward direction from 40 mm to 0 mm. It means the follower is moving in a downward direction. So I can call it as a return motion of the follower. And for the next, from 270 to 360 degree. So again, there is no movement of the follower. It means the distance traveled by the follower is 0. But the cam will be rotating. So I can call this as dwell. It means if the follower motion is of this kind, it means initially it is a dwell, there is no movement. After that, there is a rise in the follower. Again, there is a dwell. Again, the follower is going to move in a downward direction. That is nothing but a return. After that, again the follower is under rest. If certain follower is following this path, so I can call that cam and follower as dwell, rise, dwell, return, and dwell. So this is the first classification of the cam. So based on the type of the follower motion. Correct? You can see according to the type of follower motion. I'm considering the criteria that follower motion. Okay. So this was DRD. I hope this is clear. And I'll go to the next one. Okay, if you want, you can take this drawing paragraph. The second classification, that is DRRD cams. Again, I'll take the same displacement diagram. Along the x-axis, I'm going to plot the cam rotation angle from 0 degree to 360. And along y-axis, I'm going to plot the displacement of the follower. Same thing, whatever I have discussed in the previous slide. That is the distance traveled by the follower from 0 to 40 mm. For example, you can take 0 mm to 40 mm. The follower is moving in upward and downward direction. And the angle that is covered by the cam is from 0 to 360. Okay, you can take this as 0, 90, 180, 270 and 360. Okay, so in this graph you can observe that. So for initially for 90 degree, you can take this as a 90 degree, for example. Whenever the cam is rotating through an angle 0 to 90, there is no movement of the follower. The follower is under rest. It means the displacement of the follower is 0. There is no distance traveled. Okay, so I can call it as a dwell time during the first 90-degree rotation of the cam. Again, the cam starts rotating from 90 to 180. So in that case, in that time, the follower is moving in upward direction. Okay, the follower is moving in a upward direction. This is nothing but a rise. The rise of the follower means you can see the distance traveled by the follower is 40 mm. Okay, this is a 40 mm. After that, it is not taking rest. Immediately, it is coming down for the next uh, angle of the cam. You can take this as 180 to 270. During that time, the follower is coming down. So without taking any rest, okay, it is coming down. Okay, so this is nothing but a return of the follower in a downward direction from 40 mm to 0 mm. Again, for the next 90 degree of cam rotation, that is from 270 to 360, there is no movement of the follower. It means the displacement of follower is 0. It means I can call this period as dwell period. You can see the pattern of this curve is again dwell, rise, return, and dwell. If you are observing such a graph from the particular cam and follower, I can call that particular cam as a TRRD cam. It means dwell, rise, return, and dwell. So this is the pattern of the follower. The movement of the follower is in this type. So just take the drawing of this one. Otherwise, I'll share this notes in the Google Classroom. You can take afterwards also. And if this is clear, I'll go to the last one. That is nothing but rise, return, and rise cam. Okay. Again, I'll take the same displacement diagram along the x-axis. I'm going to plot the cam rotation angle from 0 to 360, and along y-axis, I'm going to plot displacement of the follower, the distance traveled by the follower. So in this graph, you can observe that the pattern of the motion of the follower is, can see initially it is rising. Okay, whenever the cam starts rotating, immediately the follower also starts moving in upward direction. Okay, from 0 mm to 40 mm. Okay, so during the rotation of the cam, so it is rising. After that, it is not taking rest. Okay, immediately it will come down. Again it is rising, again it is returning. It means there is no dwell time. In this type of cam, the follower will not take any rest in between. It is continuously moving up, down. Okay, it means rise and return, rise and return. If you're observing such a pattern of the follower movement, I can call it as a rise, return, rise cam. Okay, so it means based on the type of follower motion, we are going to classify the cams as a dwell, rise, dwell, return, and dwell cam. And the second one is dwell, rise, return, and dwell cam. But in this case, there is no dwell at all. Continuously, the follower is moving. It means it is rising, it is returning, it is rising, okay, and returning. Okay, these are the three classifications which comes under the first criteria. That is according to the type of follower motion. Then I'll go to the next one, that is according to the shape of the cams. Based on the shape of the cams, I'm going to classify the cam and follower as wedge and flat cams, and the second one as radial or disc cams, and the third one is a cylindrical cams, and the fourth one is a globoidal cams. Again, in the globoidal, there are two types. One is a convex type, and one more is concave type. And the last one is spherical cams. Okay, so please note down this second classification. I'll start with this first one, that is wedge and flat cams. Wedge and flat cams. So remember, the second criteria is based on the shape of the cam. I'm not going to consider the shape of the follower. Okay, because this is the classification of cams, not the follower. Okay. I'll start with the first one, that is the wedge and flat cams. Yeah. So this is the first classification based on the criteria that based on the shape of the cam. So you can observe that only just concentrate about the shape of the cam, not the follower. Okay. In the previous class, we have discussed, we have classified the followers based on whether it is a knife edge, it is a roller type, okay, it is a spherical face, based on the shape of the follower. But in this case, I'm going to consider, I'm going to consider the shape of the cam. Just make it as a wedge cams. Just a minor correction. Okay, so this is a wedge cam. So first I'll show the animation so that we can visualize the kind of motion the cam has and the kind of the follower it has. And you can see in the animation the shape of the cam is in the form of a wedge shape. Okay, it means the below portion or the bottom portion of the cam is perfectly flat and the top portion of the cam is inclined. So I can call this as a wedge shape. Okay, a wedge. And the previous class we have discussed the we have seen the cams which are in the form of a spherical type, which are in the form of a non-circular nature, which is having a rotary motion. But in this case, you can observe that the cam is not in the form of a circle. It is in the form of a wedge cam, wedge shape, and it is not rotating. It is moving in a straight line direction from left to right and right to left along the x-axis, or horizontal direction, you can see. And you can see, you can observe the output motion is, it is a reciprocating type in a vertical direction. So I can say that it is a simplest type of cam in which the wedge shaped cam, it moves from left to right and right to left, so that I can get the output as a translated motion in upward and downward direction. Okay, so this is the classification of the cam based on shape of this cam. Okay, I'm going to consider the shape of this cam is in the form of a wedge, so I can call it as a wedge cam. If you want the actual diagram of this wedge cam, you can show the schematic diagram of this wedge cam. It is also called as a flat cam also. Both are correct. Okay, in the examination you can draw this one. So this is the wedge shaped cam, which is having a roller at the bottom portion so that it can move smoothly from this direction to this direction along horizontal. Okay, and this is the follower, which is in contact with this wedge cam, and these are the frames, and this follower is again connected to a spring so that I can maintain a proper contact between this follower and cam. Okay, so this is about the wedge and flat cams, and I'll go with the next one, radial or disc cams. Radial or disc cams. Just copy this figure. Already I've discussed this in the classification of followers. As I discussed, the radial means can see the axis of this follower is in line, or it is passing through the center of this camshaft. So it is called as a radial cam. Okay. Also you can see the shape of this cam is not like this. It is not in the form of a wedge shape. Okay. It is in the form of a circular nature. It is in the form of a non-circular nature. It can call it as an elliptical shape. Okay. So the features of these radial disc cams is the follower axis passes through the center of camshaft. Also, one more thing is the axis of this follower is perpendicular to the axis of this camshaft. You can see the axis of this shaft is perpendicular to the screen. Okay, you can say it is perpendicular to the plain paper. Okay, the axis of this camshaft is perpendicular with respect to the follower axis. These are the two features of this radial or disc cams. Again, I can show the animation so that which are the disc or the radial cams. So all these three things comes under radial or disc cams. This is the first one. So this is nothing but a roller type of a cam and follower, and I'm going to consider only the axis of the follower. It should be in line with the center of this camshaft. Also, you can see the follower axis. It means the follower is moving in a direction such that it is perpendicular to the axis of this camshaft. Okay, and you can consider the next one, which is of a spherical type of a cam and follower. Again, just consider the axis of this follower is in line with the center of this camshaft. And this is also a flat faced cam and follower. So these are nothing but a radial or disc cams. Okay, radial or disc cams. It means the shape of the cam is not in the form of a wedge shape. It is not a spherical type. It is not of a cylindrical type. It is not a concave shape. It means you can say it is an elliptical shape approximately, not exactly. So I can call it as a radial or disc cams. And I'll go to the next one. So the next one is a cylindrical cam. As the name suggests, the shape of the cam is in the form of a cylinder. You can take this one. So this is nothing but a cylindrical cam, and it is having a one groove around its periphery. Around its periphery, the cylindrical cam is having a groove, and in that groove, a follower is fixed or a follower is attached. It means as the can see the animation, and this cylindrical cam is connected to a shaft and motor. As the motor starts rotating, the cylindrical cam also starts rotating. Okay, since the follower is attached to the groove of this cylindrical cam, so it will start moving in a horizontal direction. Okay, it means the input motion is a rotary type and the output motion is linear type. As I said, based on the shape of the cam, this is the third classification, that is cylindrical cam. Why it is called as a cylindrical cam? The shape of this cam is in the form of a cylinder with a groove, and hence I can call it as a cylindrical cam. And if you want the actual sketch of this cylindrical cam is the same thing. This is the axis of this cylinder, a cylindrical cam. So it is rotating about its own axis, and the output motion is translatory or a linear direction. Okay, it means in this case you can consider that the axis of this cam and the axis of this follower both are parallel to each other. But as in the case of radial cam, so the axis of this camshaft will be perpendicular to the paper. Okay, and the axis of this follower is in a vertical direction. Both are perpendicular. This is like this, and the axis of the cam is perpendicular to the paper or the screen. Hence it is called as a radial or disc cams. But in this case, can consider this cylindrical cam. The axis of this cylindrical cam and the axis of this follower both are parallel to each other. That's why it is called as cylindrical cam. The input motion is a rotary type and the output motion is a linear type along the x-axis. So this is about a cylindrical cam. Next one, that is globoidal cams. The next one is globoidal cams. So this is the fourth classification of the second criteria. So based on the shape of this cam. So in the previous slide you have seen a cylindrical type, but in this case it is in the form of a convex shape. Again, the working principle is same. This cam is connected to a shaft and the shaft is again connected to the motor. As the motor starts rotating, this cam also starts rotating. And since it is having a groove, and inside this groove, with respect to that groove, the follower is attached. Okay, you can see the animation of this convex shape globoidal cam. We are giving the input motion as a rotary type and the output motion is oscillating. I'm not worrying about the type of follower motion, only I'm going to consider the shape of this cam. Okay, since it is in the form of a convex shape, it comes under globoidal cam. And one more example of this globoidal cam is a concave shape cam. You can see the animation. Again, the working principle is same. The shape of this cam is in the form of a concave shape and it is having a groove. With respect to the groove, the follower is attached. As the cam starts rotating, the follower starts oscillating from this direction to this direction. Just try to watch both the animation once again. Okay, so these are the features of this globoidal cams. Yeah, then I'll go to the last one, that is the spherical cams. So you can observe the shape of the cam is in the form of a sphere. Okay, it is a spherical type. Again, it is connected to a shaft and motor. As the sphere starts rotating like this, you can see the input motion is a rotary type, and this sphere is having again a groove around its periphery. And with respect to this groove, the follower starts oscillating. Okay, it means the input motion is the rotary type and the output is oscillating. But I'm not going to consider the type of follower motion. Only I'm going to consider the shape of this cam. Since the shape of the cam is in the form of a sphere, I can call it as a spherical cam. So these are the 5 classifications based on the shape of the cams. If you want the schematic image of these two, that is a globoidal cam. In the examination, you can draw this one. So this is the axis of the cam, or the camshaft, and this is the axis of the oscillating follower. Okay, you can see all these cams. It means a cylindrical cam. You can see the axis of the cam and the axis of the follower are parallel to each other. In this case, they are at some angle. The axis of cam and the axis of the oscillating follower, they are at some angle. It's also the same thing. This is the convex type globoidal cam, and this is the concave type globoidal cam, and this is the spherical type. Now, all these 3 things, you can see the axis of camshaft and the axis of this follower, they are at some angle. They are not perpendicular. Okay. But in the case of a radial cam, you can see the axis of this follower and the axis of the camshaft, they are perpendicular to each other. That is the only difference between this radial cams and the remaining 3. Okay. So these are the 5 types of classification of cams based on the shape of the cam. Okay. The first one is a flat cams or the wedge cam. Second one is a radial type. Third one is a cylindrical type. Fourth one is a globoidal. It may be in the form of a convex shape or it may be a concave shape. The last one is spherical cam. And the last one I'm going to consider the third criteria according to the type of constraint of the follower. So better I can go with the slides. So this is the third classification. Just note down these two classifications. First one is a positive dry cams and one more is a preloaded spring cams. The third criteria is that based on the type of constraint of the follower. It means what is the kind of restriction these cams have. We can classify into two types. One is a positive drive cams, one more is a preloaded spring cams. I'll go with this one, that is a positive drive cam. So you can see this is nothing but a globoidal cam, correct? And there is no, you can see the contact between the cam and the follower is maintained with the help of a groove, correct? There is no external force or there is no spring force which is required to maintain the contact between these cam and follower. Again, you can take this concave shape globoidal cam. So there is no use of spring force. Only due to the this groove which is provided on the periphery of this cam, so the contact is maintained. Also, you can take the cylindrical cam. So there is no use of spring force, and this also same the spherical cam. It means all these four cams comes under positive drive cams. All these four types of cams, they'll come under positive drive cam. It means in this type of cams there is no requirement of external force or a spring force to maintain the contact between cam and follower. Only with the help of a groove which is provided on the periphery or on the surface of the cam, we are going to maintain the contact between the cam and follower. There is no use of spring force, so hence these are nothing but these are the cams which do not require any external forces to maintain the contact between cam and follower. These four types comes under positive drive cams. And what about the last one, that is a preloaded spring cams? So you can see the follower is connected to a spring force so that I can maintain a proper contact between the follower and the cam. There is no groove at all. And in this also a roller type of a cam and follower, you can see the follower is attached with a spring force, the spring. And this is the spherical type, the spherical face, the cam and follower. Again, you can see there is a provision of a spring around this follower. And this one is a flat faced cam and follower. Again, you can observe the presence of this spring. It means in all these four types of cams, there is a requirement of a spring force or external force so that I can maintain a proper contact between a cam and follower. It means all are loaded with a spring, so I can call it as a preloaded spring cams. So this is the difference between the positive drive cam and preloaded spring cams. So these are the four examples of preloaded spring cams. Yeah, and this is all about the classification of cams, and we have discussed the first one based on the type of follower motion. There are three types, and the second one based on the shape of the cam. Again, there are five types. The last one according to the type of constraint the follower has. It means if you are maintaining the contact between cam and follower with the help of a groove and without using any spring force, you can call it as a positive drive cams. And the examples are this one, globoidal cams of convex shape, and one more is concave shape, and cylindrical cam and the spherical cam. In all these four types, there is no use of a spring force. Only with the help of this groove, which is provided on the circumference or the surface of these cam, there is a proper contact between a follower and cam is maintained. Okay, these are nothing but a positive drive cams. And the last one was the preloaded spring cams. It means with the help of a spring force, we are going to maintain a contact between cam and follower. So all these four comes under preloaded spring cams. So if it is clear, I'll go with the last topic, that is types of motion of the follower. So please note down these four types of motion of the follower. And while explaining the features of the cam, I explained that the cam will be having a uniform speed, correct? Always the cam will be having, it will be rotating with a uniform speed. But what about this follower? You can see in the different types of followers, the velocity of this follower changes. Okay, during the upward motion of the follower, that is a rising of the follower, the velocity may be different. It may be 2 centimeter per second. During the downward motion of the follower, the speed may be different, that it may be 4 centimeter per second. Again, it will take some rest in between. It means the speed of this or the motion of this follower is not uniform. Okay, and what are those different types of the follower motions? So these are the four important follower motions. The first one is a uniform velocity. It means if the follower is moving with a uniform velocity, I can call it as a uniform velocity follower. And one more is a uniform acceleration and retardation of follower. So in shortcut, I can call it as a UARM. The next one is a simple harmonic motion, that is accession. The last one is a cycloidal motion. So these are the four different motions of the follower. Based on the requirement, based on the applications where you are using this cam or a follower, can decide which one is required. Okay, I'll go with the first one, that is a uniform velocity. And remember, the keyword is the type of follower motion. Remember, okay, the first one is uniform velocity follower, this one. I'm not worrying about this cam because it is having always a uniform speed. Sometimes, what about this follower? It may be, sometimes it may be having a uniform velocity, sometimes it may be having a uniform acceleration and retardation motion. Sometimes the kind of motion the follower has is a simple harmonic, and last one is cycloid. It means I'm to decide which kind of follower motion I want, so that I can use this cam and follower for particular applications. It means for textile industry, for textile machines, I want a different speed of the follower, and for uh, controlling the feed mechanism of a automatic lathe, I want a different speed of this follower, and for automobile engines, to control the inlet, the motion of the inlet wall and the exhaust wall, I want different timing or a different speed of this follower. So based on applications where you're using, can decide which is required, whether you want a follower with uniform velocity or the follower with uniform acceleration and retardation motion. And the third one, a simple harmonic motion, and the fourth one is cycloidal motion. I'll go with the first one. And while solving the numerical on the cam design, I'm going to explain in detail what is exactly this outstroke, dwell time, return stroke, and again dwell time. Okay. And the first one, you can see the first drawing. This is nothing but a displacement diagram. It means along the x-axis, you're plotting angular displacement of the cam, that is from 0 to 360. And along y-axis, you're going to plot the displacement or the distance traveled by the follower, which is indicated with small letter s. Okay, and this is nothing but a velocity of the cam and follower. So this is the velocity diagram. Again, along the x-axis, I'm going to consider the angular displacement from 0 to 360. But along y-axis, instead of a displacement, I'm going to plot the velocity. Using the formula, you can calculate the velocity of the follower. And with those values, I'm going to plot the velocity versus angular displacement. As the name suggests, you can see the uniform velocity of the follower. After plotting this graph, you can observe that the speed or the velocity of the follower is uniform. During the rise of the follower, whenever the follower is moving in upward direction, you can see the velocity is uniform, it is constant. Okay. Again, during the return motion, whenever the follower is coming down, that is a return motion of the follower, you can see the velocity is uniform. If the speed of the follower is uniform, I can call it as a uniform velocity of the follower. Now, how to plot this displacement diagram, I'll explain here while solving the numericals. How to divide the outstroke into 6 equal parts and how to draw this one. And how to divide the return stroke into 6 equal parts. And how to draw this displacement during the return motion. For different stroke lengths and for different outstroke angle and return stroke angle, I'm going to explain in detail while solving the numericals. Don't worry about that one. Only just consider why it is called as a uniform velocity of the follower. Since the follower is having a uniform velocity during the upward motion, that is a rise of the follower, and during the return of the follower, the velocity is constant. You can call it as a uniform velocity of the follower. The second one, is nothing but a uniform acceleration and a retardation follower. So you can call it as a UARM. The problem directly they will mention this UARM. The follower is having a UARM just to design the cam. Okay. So based on this requirement, you have to decide the shape of the cam. You have to design the cam based on what is the requirement of the follower motion. In this case, I want the follower has to move with uniform acceleration and retardation, that is UARM. So this is the first one is nothing but a displacement diagram. Means the distance traveled by the follower is considered along y-axis and the cam rotation angle is considered along x-axis from 0 to 360. Okay, you can see the S means the distance, the maximum distance that is covered by the follower from 0 to some distance. You can see 40 mm. And you can take the second one, that is a velocity versus angular displacement. Okay, it means along the x-axis I'm going to consider this angular displacement. Here also angular displacement, and here also the angular displacement. So this is the velocity diagram, this is the acceleration diagram. Okay, now how to plot this displacement diagram for this uniform acceleration and retardation motion, I'll explain while solving the problems on this UARM type. Okay, don't worry about this one. And why it is called as a uniform acceleration and retardation motion. So since it is since you're calling this as a uniform acceleration, I'm going to consider this acceleration diagram. Okay, and you can observe that during the rise of this cam, so this is the rising, this is the dwell period, this is the return. You can see the acceleration is uniform. The acceleration is uniform acceleration and it is uniform retardation. Retardation means the negative acceleration. Okay, so you can see this is the uniform it is a velocity and angular displacement. It means there is a variation of the velocity. It is uniform velocity. It means there is no change in the velocity. It means the rate of change of velocity is uniform. It is gradually increasing and gradually decreasing. It means if the rate of change of velocity is uniform, it means the acceleration will be same. Acceleration will be same. So from this graph, that is acceleration versus angular displacement, you can consider that if the acceleration is uniform and the deceleration is nothing but a retardation is also uniform during the rising time of the follower, and during the returning of the follower also same. Uniform retardation and uniform acceleration. Okay. Retardation is nothing but a deceleration. Okay. And for particular type of cam and follower, if you are getting this pattern of acceleration diagram, I can classify that particular follower as uniform acceleration and retardation follower. Okay. And the next one is a simple harmonic motion. That is the SHM, simple harmonic motion of the follower. And again, this is the displacement diagram versus the angular displacement. And this is the velocity versus angular displacement. And I would consider this curve which is obtained in the velocity diagram. Okay, since it is having a sine curve during the rising of the follower, so this is the rising of the follower, and this is the dwell time. Again, the follower is moving in a downward direction. Again, dwell time. Okay, so this is the method using a semicircle method, how to plot this displacement diagram for a simple harmonic motion. Again, I'll discuss in detail while solving the numericals on this simple harmonic motion follower. Okay, since the type of motion is in the form of a sine curve, which is nothing but a harmonic function, so I can call this type of a follower as a simple harmonic motion. Okay, only just observe the velocity diagram. So if you are getting a sine curve or any harmonic functions, so I can call that particular type of cam and follower as simple harmonic motion. The last one is a cycloidal motion. Cycloidal motion. Whenever the displacement of the follower follows this type of pattern, you can see this type of a pattern. It is having a smooth curve. There is no sudden rise of the follower or sudden fall of the follower. So this is nothing but a displacement. It is having a smooth displacement. It is having a smooth displacement, and this is plotted. This displacement diagram is plotted using a circle method, and you can consider the circumference of this circle will be equal to the displacement of the follower. For example, if the follower is moving from 0 to 40 mm, so this is nothing but a small letter, this S, alphabet S, it means the stroke length of the follower is 40 mm, and I would consider the circumference, that is a 2 pi r, which is equal to the displacement of the follower. You can take here. It means the displacement or the stroke length of the follower, that is S, it is equal to the circumference of this circle. It means S is equal to 2 pi r. When you consider this criteria and using the circle method, you are going to plot this diagram. After that, if you are getting this smooth curve, smooth displacement curve, then that particular type of motion is called as a cycloidal motion. It means it is an optimized motion of all different varieties of follower motion. It is not having a uniform velocity, it is not having a uniform acceleration and retardation, but it is having a combination of all the optimized pattern. You can see there is no sudden rise in the follower. It is taking a smooth direction. Okay, it is a smoothly rising. Again, it is a dwell, and it is smoothly returning back to its original position. This is a rise, a dwell, a return, and a dwell. Means if you are satisfying this condition, it means the displacement of this follower is equal to the circumference of this circle, that is a 2 pi r. Then that particular type of pattern you'll get is nothing but a cycloidal motion, and such followers comes under cycloidal motion follower, and this is the most selected type of cycloidal motion in different applications in the aircraft industry or in aircraft engines, and in the automobile industries. We are going to select this kind of cycloidal motion because for high speeds the cycloidal curve gives the best surface of the cam. The cam will be designed in the best manner when you're going to select this kind of follower motion, and it has the lowest vibrations. The whatever the vibrations which are getting from the follower, they are less, and it is having a less wear. And whatever the induced stress are, they're also less, and it is having a less noise and shocks. Okay, so that there will not be any damage to the cam and follower. So these are the features of this cycloidal motion, and these are the list of formula. Please note down how to calculate the maximum velocity and maximum acceleration for these three type of follower motions. In the examination, you'll be asked to draw the cam and the cam profile for these type of follower motion, whatever I explained in the previous slide. Okay, it means if the follower is having uniform acceleration and retardation motion, what is the maximum velocity? You can take this formula. And what is the maximum acceleration? Okay, this V naught max indicates the O indicates the outstroke. Outstroke means the follower is rising, means the follower is moving in upward direction. The R indicates, the suffix R indicates the follower is moving in a downward direction. It means the return stroke. During the outward motion, during the rising of the follower, what is the maximum velocity? Okay, and maximum acceleration. And what is the maximum velocity during the return stroke, during the downward motion of the follower? That is nothing but VR max. Similarly, for simple harmonic motion, during outstroke and during return stroke, what is the maximum velocity and what is the maximum acceleration? And finally, same thing for cycloidal motion. Please note down these formulas. Okay, and omega indicates the angular velocity, of a follower. Okay, or can take angular velocity of the cam. The cam is rotating with a certain speed. The speed rotation of the cam in the form of RPM. Omega indicates the angular velocity of the cam. Okay, this will be given. The speed of the cam will be given. The stroke length of the cam will be given. It should be in meters. And what is the outstroke angle? It means the angle that is covered by the cam during which the follower is moving in upward direction. Upward means the outstroke. The downward motion means the return stroke. Both are same. And make sure that the angle should be in radians. The angle should be in radians. Please note down these formulas, and in the next class I'll start with the numericals. So based on different conditions, based on whether you want to design the cam profile for a knife edge type of a follower, or a roller type of follower, or the flat faced follower, and based on whether you want a uniform acceleration and a retardation motion of the follower, whether you want a simple harmonic motion, and whether you want a cycloidal motion. So you are going to calculate the maximum velocity and maximum acceleration during outstroke and during return stroke. O means the outstroke. Whenever the follower is moving in upward direction, it means the follower is rising. Return stroke means the follower is moving in a downward direction. Means it is returning back to its original position. Okay. And if it is clear, I'll wind up today's class. Okay. And it means in the today's class we have discussed the classification of cams. Correct. We have discussed the classification of cams on different criteria. So these are a different classification of cams. Correct. So these are examples of radial and disc cams. Okay. And also we have discussed the positive drive cams. These are the 4 examples. All these 4 comes under positive drive cams, and these are nothing but a preloaded spring cams. And finally, we have discussed different types of follower motions. Okay, whether the follower is having a uniform velocity, and whether the follower is having a uniform acceleration and a retardation, and it is having a simple harmonic and a cycloidal motion. Okay, these are nothing but a displacement diagram and a velocity diagram of the follower. Okay, for this uniform velocity, for uniform acceleration and the retardation motion, you can observe this one, the acceleration diagram. It is uniform, means the rate of change of velocity is uniform, means there is a gradual increase in velocity and gradual decrease in the velocity. So this is nothing but a maximum velocity. So whatever I have listed the formula, using that formula you can calculate the maximum velocity and maximum acceleration. And this is for a simple harmonic motion, and finally cycloidal motion. And in the next class, I'll start with the numericals on CAM design. Okay, and everything is clear, I hope. And I'll wind up today's class. Okay, thank you.